All right, so now we've done quite a bit of arithmetic. We're going to get into some terminology. Now, as I said earlier, it's the terminology that's going to get you in a physics course. You've got to know the lingo. So we're going to spend some time on the lingo, and we will get back to some more arithmetic, but that's a little bit later. So before we do anything else, we're going to do something normal that I would normally do in class, and I can't do it the way I would normally like to do this. So you're going to have to kind of bear with me and not cheat. So here's what I want you to do. I want you to grab a piece of paper or use the back side of one of the pages in your book. And here's your assignment. I want you to come up with the definition of time. What is time? Give yourself, hit pause and give yourself about 2 minutes to come up with an answer. Now, don't Google it. That defeats the whole purpose. Don't Google the answer. The idea of this is to come up with your best native understanding of how to define time. So here we go. What is time? Hit pause. Okay. So presumably you hit pause, you came up with your definition of time, and you didn't cheat, and you didn't Google it. We'll get to that in just a few minutes. But right now we're on page 22 in the workbook. We're going to get into some terminology. The first thing we're going to talk about is displacement. Displacement, we have two definitions that we're going to use. Length and direction. Or distance and direction. That's the definition of displacement. Now the direction piece of this we'll get into a little bit later when we get into vectors. We're not there yet. But those are the two definitions that we're going to use to define displacement. The symbol that we will use is lowercase letter s. And why do we do that? Quite frankly, it goes to which textbook is being used. And at SMCC, the majority of the textbooks that are on our campus use lowercase letter s as the symbol. You know, other textbooks might use a capital D, but this is what we're going to use just to stay consistent. Standard units. This is going to take some work too. We have to use standard units when we're defining or describing or measuring these different quantities. So the standard units, British or US standard, that's us, is a foot, abbreviated like so, and metric is a meter. Abbreviated like so. Not kilometers, not miles, not inches. It's going to be either feet or meters. That's it. And the reason for that is these are the units that we're going to be plugging into Sir Isaac Newton's formulas. And if you put the wrong units in, it's just going to blow everything up. Okay. Now, also note that in this context, displacement does not refer to volume. So context is going to drive a lot of this. So in this context, this is what displacement is referring to. The next thing we're going to talk about is force. All right. Definition of force. We'll use Sir Isaac's definition of a force. A push or pull. That's Sir Isaac's definition of a force, a push or a pull. And I'm going to add my own definition there just to kind of clarify a little bit more. That which may affect motion. That's what a force is. Okay, know them both. The symbol we use is a big old capital F. And the standard units, British or US standard, is a pound. Abbreviated like so, LB. And metric is named after the great man himself. It is a Newton. Abbreviated like so. Now, note at the bottom of the page here, since a pound is a unit of force, then it is not a measure of mass. We have to be clear about this. A pound is not a unit of mass. It's a measure of force. Okay. Next page, page 23. Mass. We're going to have several definitions. Sir Isaac had a couple of definitions. The first one goes like this. A quantity of material. But he had another definition as well. A measure of inertia. We'll come back to that. And the third definition of mass that you will encounter in any number of college textbooks stuff. Yeah, I'm not making that up. Stuff. All right. Now, what about this idea of inertia? Resistance to a change in motion. All right. Standard units, British or US standard, is a slug. I'm not making this up. We hardly ever use it, but that's what it is. And again, just to emphasize, not a pound. And metric is a kilogram. Not a gram. A kilogram. And again, the idea is, what are we going to be sticking into Sir Isaac's formulas? And so that's what we'll be using. Now, I want to be clear about this, understanding this idea of mass versus force. I'd like you to go ahead and flip back to the previous page where we talked about force and make a little note to yourself. Okay, so back on to the previous page where we talk about force. make a note of this. Weight is a measure of force. Here's a way to understand this. We'll do a little science fiction here. What we're going to do is we're going to do a little Star Trek, and we're going to beam you out into space, floating in space. Don't worry, you got a spacesuit on, so you're all right. So there you are, floating in space. You are whatless? Weightless. You are weightless, all right? But you still got mass. You got stuff. So there you are, floating in space. You're weightless. And you look to your right and you see there's a basketball floating beside you. So you reach up and you push on the basketball. What happens? Well, the basketball is going to move off. You might move a little bit, but the basketball's going to do most of the moving. Why? Because it has a whole lot less stuff and therefore less inertia, less resistance to a change in motion. Even though it has mass, it's got a lot less mass. And remember, both you and the basketball are weightless. Meanwhile, you look to your left and you see floating beside you a United States Navy aircraft carrier, or as we like to call it, 100,000 tons of diplomacy. And so you reach up with your left hand and you push on the barnacle encrusted hull of that aircraft carrier and you push. What happens? You move and the carrier doesn't budge at all. Why? Well, because it's got a whole hell of a lot more mass, a hell of a lot more resistance to a change in motion, a hell of a lot more inertia. Yet, all three objects, you, the aircraft carrier, and the basketball are all weightless, but because of the different amount of mass that each of you have, you're going to resist a change in motion at a different level. Okay, so that's one way to keep it straight. The next item is volume. Now, how do we define volume? Well, it's an amount of space. As simple as that. An amount of space. Standard units for British or US standard, a cubic foot, or abbreviated like so. And metric is a cubic meter. Abbreviated like so. Note, liters are also frequently used to measure volume in metric terms, but they are no longer considered a standard unit. They got demoted some years back, but we do use them. They're just not the standard unit. So that's the standard unit of volume. Now, last on the page, time. Hopefully you had a little fun with that, trying to define time. What is it? Well, here's the definition that we are going to use. That's the definition that we will use for time. That which we measure with a clock. And it's in quotation marks because it's a quote. Who came up with that one? This guy, you may have heard of him. So, yeah. Time is that which we measure with a clock, according to Albert Einstein, the man who literally rewrote the book on how we look at time. So I say, if that's good enough for Big Al, it ought to be pretty good for the rest of us. Albert Einstein, you should know, his overarching thesis was that we should ultimately be able to explain anything in the universe simply. he was an adherent of the KISS principle. KISS, keep it simple, stupid. Well, this is what Albert Einstein was all about, finding an ultimately simple explanation for how the universe ticks. Albert Einstein also did say length is that which we measure with a stick. And he also did say, and it's in the book somewhere, he also did say, and I quote, this is not urban legend, he really did say this, anyone who can drive an automobile safely while kissing a pretty girl is clearly not giving the kiss the attention it deserves. Wise words from Albert Einstein. All right, so there are our definitions. These are the ones that you need to know. These have to become part of your vocabulary. You have to be very, very clear on those. And in the next lesson, we'll talk about how we're going to measure them and convert them from, say, miles per hour into feet per second and so on.